morning. So let's start this Friday morning session on time. And thank you all for coming to session B4.8, Small Sats Symposium. And this is the session on small satellites for deep space exploration. First of all, I'd like to thank Renee. Renee and I have been, my name is Leon Alkalai, and Renee and I have been chairing this session for, I think, about a decade now, almost 10 years. And this is a standard session on using small sats, CubeSats, nanosats, particularly for going beyond Earth orbit. So with that, I'm going to open up this session, and Renee, to you.
Yeah, also welcome from my side. We are very glad that we have this attendance on Friday morning, the last day of the IAC, and let me quickly introduce our first speaker, which is Dr. Leon Alkalai, giving the keynote for this symposium. Dr. Alkalai is a JPL fellow and has been working in mission formulation at JPL for Moon, Mars, Venus, and beyond. And he's giving the keynote titled An Overview of CubeSat Projects at JPL, Past, Present, and Future. Please.
Thank you, Renee. So my understanding is that we have very few cancellations today.
We have very few cancellations, and I would like to inform you that we changed the order of the papers a little bit. Papers 6, 7, and 11 are two colleagues who have to fly out very early. I think we saw this over the week, and we will put them right after Dr. Alkalai and then proceed with the order after that.
Very good. Thank you. And so let me proceed. I'll be giving an overview of this topic of CubeSats and nanosats at JPL, and particularly for deep space exploration, but you'll see it includes Earth science as well. What you see here on the picture is a picture of JPL on a very unique day, and with snow in the mountains and beautiful scenery in front. So this is a few miles from Pasadena. If any one of you have had a chance to visit, JPL is a division of Caltech, so JPLers are Caltech employees. We're also a NASA center. We're an FFRDC, a federally funded research and development center, owned by Caltech and managed by Caltech for NASA. So that's just a brief overview of where I work, and I've been there for now 26 years, mainly focusing on mission formulation. And early in my career, first 10 years, I worked on advanced technologies, microsystems, including topics like nanosats and CubeSats. So I'd like to give an overview of what's going on at JPL. So this is somewhat JPL-centric. I want to also emphasize that there's quite a large effort going on across the agency at NASA Ames, at Goddard, at other NASA centers. So it's not exclusive at all by any means to JPL, and I don't want to leave that impression. But this talk was specific on what's going on at JPL because the topic is focused on deep space exploration. Also, let me not forget that I'd like to acknowledge my two co-authors in this overview paper, Charles Norton and Tony Freeman, both at JPL, and they both have a significant role at JPL in one form or another in the area of nanosats and CubeSats. One thing that I'd like to emphasize is that at least many of us at JPL do not feel that nanosats and CubeSats are a solution to everything. And there may be people like that, but we clearly feel that has to be a balance between where nanosats really have a unique value to add, and it's clearly not in every application area. This slide shows a spectrum of applications from flagship class missions. These are perhaps over $1 billion, $2 billion kind of missions, to what we call large, medium class, mini satellites, and then CubeSats, which are in this low end of mass, and in many cases low end of performance, but in some cases as well, it can provide performance that even exceeds those of much larger missions, and those would be those unique niche areas where nanosats can indeed provide high value. I'd like to hit this topic right up front with what's going on at JPL in terms of this topic. And you can see here roughly about a dozen projects, all either have launched or are about to launch, or different phases of development from phase A to phase E. And this is quite a unique situation. And what's also not shown here is that there's a whole body or a whole set of nanosat mission concepts being developed in a concept pipeline. To give you an example, in the most recently awarded Discovery class that NASA selected 5 Discovery missions, of which 3 at JPL and 2 at Goddard. In that offering, when JPL submitted close to a dozen proposals, and there was an opportunity given by NASA to propose technology demonstration opportunities. Well, JPL made a point of every proposal, including in some form or another, a CubeSat adjunct spacecraft to the primary mission in order to enhance or provide an opportunity beyond the primary science mission. So we've really embraced this, this topic in a kind of comprehensive way to see where it goes and so on. So this is not a one-time a commitment. It's not a small effort. It's a pretty pervasive or broad effort to introduce these nanosats into deep space. So what you see, I don't plan to go through all of these missions, but the impression that you should get is that there is a large amount of activity in this field at JPL. I will start now with Earth science, and even though this topic is intended to be more focused on deep space and planetary, the Earth science is, in fact, an essential component of planetary. And what I mean by that is that many technologies that are demonstrated in Earth science can, in fact, be then applicable to deep space. So drawing a distinct line between these are Earth science missions and these are, let's say, missions to Mars or the Moon and so on, is somewhat arbitrary or artificial, because one can demonstrate technologies, and we are demonstrating technologies in Earth science, and then using those technologies or planning them for use in planetary and heliophysics and astrophysics. So this is a launch of the SMAP Soil Moisture Active Passive Mission earlier this year in January, and in fact it launched 3 CubeSat systems, the ExoCube, Firebird, and Griffix. And each one has been launched, and here I'm going through a little bit more on 3 specific CubeSats, the NCube, the Cove2, Ipex, and Griffix. Griffix that was launched on SMAP 1. And my intention here is not to spend the small time I have in going into details on every one, but just to show you the kind of capabilities that each one of these systems is demonstrating. And you'll see in each one of these situations, JPL has partnered with outside organizations to both develop and field these CubeSats. This is the NCube Cove is with Michigan, University of Michigan, and it's used to advance the instrument signal processing technology for high data rate instruments. So you see the kind of science that is being used here, and new capabilities, new signal processing. In this case, it was with advanced Xilinx Vertex FPGA processors that are integrated into this small 1U CubeSat. Moving on to Ipex. Ipex is a partnership with Cal Poly. This is a local university, or pretty local, pretty close to in California to JPL, and a university with whom JPL has an extensive partnership program. There are many students from Cal Poly working at JPL, either in summer internships, and we have faculty visitors, a joint program with Cal Poly, so it's an ongoing relationship. Ipex was used specifically as a pipeline for demonstrating advanced autonomous operations. This is work of Steve Chen at JPL, and this is a recurring continuum of flight demonstrations using CubeSats to do automatic scheduling, target identification, feature extraction, autonomous operations. So it's a very useful capability for a principal investigator like Steve Chen, who works in the area of autonomy, to actually demonstrate the capabilities not only in a lab, but in a real small flight project in Earth, around Earth. Here's Griffix. This is a just launched in January, and then this is specifically was designed to advance detector technology for atmospheric chemistry science from GEO. And so again, this is a capability that is very exciting. It's demonstrated. It's being demonstrated in an Earth science application, but it certainly can be used in other destinations as well. I would like to show now as part of the Earth science program at NASA. In 2012, they awarded this selection of CubeSats, primarily of a 3U class. You see from MIT, APL, Goddard, Aerospace, and so on. And in 2015, this is just a few weeks ago, 2 of these have been awarded to JPL, Cirrus, and NCube. And you see others, Ohio State University, Ball Aerospace, and so on. And again, these are really capable systems on a small scale, but very capable systems, demonstrating deployable structures and various science instruments and so on and so on. So going beyond Earth, and one could easily dwell for another hour or so just on the Earth science demonstrations and applications. But going beyond Earth, it's getting quite busy. What may have been recently, up till recently, maybe 1 or 2 opportunities, now it's becoming quite exciting. And as you'll see, we're launching next March in conjunction with the InSight mission to CubeSats to Mars. We're planning missions, CubeSat missions to the moon, asteroids, small bodies, and so on. So this is kind of just a broad destination kind of description of where some of these CubeSats are being deployed. One of the first interplanetary CubeSats that we built, this is a project led by Andy Clash called INSPIRE, was primarily designed to demonstrate some of the deep space capabilities, including communication, radiation testing. And these 2 CubeSats have been built, they haven't been launched, and they're more or less, they're basically staying in storage at JPL. But they were used as they were developed and fully implemented. The technology and the capability was directly applied to the follow-on CubeSat missions, including Marco. Here you see the kind of inside development, the inside structure of the INSPIRE, all the elements and the propulsion system, the CNDH, and so on. And the INSPIRE system was used as a blueprint and as a starting point for a mission to Mars, which will launch, as I said, in March, called Marco. Marco, let me just bring that up. Marco are 2 spacecraft, basically, that will launch on the InSight, on the Atlas launch vehicle. And then these 2 CubeSats will be going to Mars separately from the cruise stage of the InSight lander that will land on Mars. It turns out that the actual coverage of the critical event of EDL on Mars is not fully covered by the existing assets on Mars because of the timing and the inclination and the orbit of the communication satellites, so around Mars, including MRO and Odyssey. So having these CubeSats fly over there and provide a link, a direct link using UHF and X-band is extremely valuable. So I just went too fast here. So these 2 satellites are basically timed to fly by exactly during EDL. The EDL will go, entry, descent, and landing will go as planned. It will communicate with the communication assets around Mars using UHF, and at the same time, the 2 CubeSats will be flying over, picking up the UHF, and providing the X-band link back to Earth in real time. So this is they're actually providing a very, very critical function that otherwise wouldn't exist because of the timing. In fact, we wouldn't get the data back until about an hour or two later if we just used the existing assets. So it's not the factor that it's not the fact that we wouldn't have coverage, we wouldn't have real-time coverage otherwise. Let me segue into another topic that is quite exciting. Over the last year or so, we've been looking at a design of a helicopter system, so for aerial mobility, using the same CubeSat technology that you've seen earlier now in Marco and other systems. I'm not going to go through the details, but just to give you the vision for where a system like this can be applied, and it's being considered, it's not yet been approved, but it's being considered as an option on the Mars 2020 rover to be deployed in situ as a scout, as a companion vehicle that can scout and look at the terrain ahead for the Mars 2020 rover. This is very serious. This is work going on right now, and if it gets approved and if the funding is in place, it will be a breakthrough demonstration of, again, a CubeSat scale technology for aerial mobility, in my opinion, much like the Mars Sojourner rover was on Pathfinder and opened up surface mobility on Mars. We're also looking at adjunct CubeSats or nanosats for missions as far as Europa. So we have the Europa Clipper project underway, and it's quite conceivable and it's quite logical, and it may not even cost too much to equip the Europa spacecraft with one or two or a few CubeSat missions that would again act as a small addition, a small kind of a burden, let's say, to the mothership, to the flagship mission. But the payoff, given the frequency of going to Europa, is really, really low. The payoff could be very high, and we are looking at examples of flybys, of probes, penetrators, and so on, that can all be implemented in the scale of a CubeSat, a 3U or 6U CubeSat. This is also showing that CubeSat technologies are not only used or applicable to Earth science and planetary. There's quite a bit of work being done right now in other parts of the science directorate, including heliophysics and astrophysics. And in the area of astrophysics, you can imagine small telescopes. They don't have the aperture, they don't have the capability of large telescopes, but their cost is very low, and they could be deployed in a very unique and specific approach to target unique science. Somewhat larger scale than this, but not too far, is the mission from Caltech. I'm blanking out Fiona Harrison's mission, the X-ray telescope. That will come back to me. That's already been flown and is doing phenomenally well. So one can build telescopes on a scale of 3U or 6U CubeSats. Moving further along, besides deploying or building these missions, JPL is investing in the infrastructure to be able to build and develop these kind of CubeSats for broad applications. We do have something explicitly called Team XC. Those who are familiar with how JPL works, we have for 20 years now something called Team X, which is a rapid mission formulation, mission design infrastructure at JPL. So we've actually broke off a smaller group of primarily very young new hires at JPL who have been working on CubeSats at universities. They come to JPL with the knowledge of even having launched a CubeSat. So we've used this young talent at JPL to formulate a new group called Team XC, and they have been developing a rapid mission formulation set of tools that are applicable only to CubeSats or nanosats. This is very important because it's not only the tools, it's also the frame of mind, It's the openness, the eagerness, the acceptance of this kind of a capability for mission formulation. So somebody who is of a completely different generation and has only designed flagship missions may not be as open as somebody who is already in the field, and so they are running this Team XC, which is actually doing a lot of good work. We've also developed an infrastructure in terms of facilities, labs, specifically for the development and testing and qualification of CubeSats. This is our CubeSat lab at JPL. And also we're developing the infrastructure in terms of stations, X-band stations, and so on at JPL as well. What I'd like to, I'm coming to a conclusion here now, is that I'd like to bring up one topic which I'm particularly interested in and concerned about, and that is that at JPL at least we're kind of inundated with all the possibilities and all the opportunities for launching different CubeSats. They seem to be appearing all over the place, somewhat in an ad hoc fashion. So we're trying to actually develop, besides all the other infrastructure that I showed so far, also what we're calling a flight portal for specifically for CubeSats and nanosats. And that means that we keep track of every launch opportunity that has the option of flying as a secondary payload, ESPA-ring, tertiary payload, commercial launches from NASA, launches from the Air Force. So there is, from what I can tell, or JPL, there is no one place that one can go to a clearinghouse of launch opportunities for Earth science, planetary, or other destinations. So we have a few people working on a website that is specifically designed so that somebody who is developing a CubeSat project can go in there and see what are all the manifest opportunities over the next few years, and then target those specifically for their tech demo or flight opportunities. So this is work in process. This is just some examples of how these CubeSats are being launched. So I will conclude by simply saying that this topic of CubeSats for deep space explorations is indeed an important one and recognized by the IAA, the Academy. And so there is a small study group looking at explicitly compiling the set of recommendations and an overview of the field of small satellites for deep space exploration. This is study group 4.16 that I lead with Pierre Busquet here, René Laufer, and Filippo Graziani from University of Rome. And also I want to bring to your attention that there was another very nice paper here from JPL by Brent Sherwood and colleagues from JPL. It was yesterday on the topic of also overview of CubeSats for deep space exploration. So I urge you to look at that paper as well. So with that, thank you very much for your attention, and I think we have...
Yeah, we definitely have time for questions. Are there questions? Yeah, please, right in front.
Okay.
Carl Brandon from Vermont Technical College. We currently have a CubeSat that's been operating for about 23 months, a CubeSat, and we're working on the lunar ice cube, which will be going on the Space Launch System. And I was just at JPL getting training in the advanced multi-mission operations software and space network. And I was wondering, are there any other outside CubeSat projects that are using the tools that we're not using, the software, ground software, software, and deep space network communication? And part of this
Yeah. So the short answer is yes. The longer answer is that we have work going on in two different areas at JPL, two different directorates. One is in the Interplanetary Network Directorate, that's the DSN, the Deep Space Network. They have an explicit effort just for support of CubeSats from a deep space communications point of view. So that's one branch of the answer, yes. Then we have in the Engineering and Science Directorate, in the Mission Operations Directorate, we have a separate effort going on just to provide the multi-mission operations infrastructure for CubeSats. So the answer is yes on both of those, deep space communication protocols, in both at the physical level and software level, and then on the mission operations, we have support. And if you send me an email, I can put you in touch with the people who are doing that.
There was another question there.
Yeah. All these CubeSats, most of the time, they will be announced as additional passengers, so they will end up somewhere in an earth-bounded orbit, and they need then quite some delta V in order to leave the Earth and to reach the target in interplanetary space. So they have probably very high delta V requirements. Is this, can it easily accommodated in such CubeSats?
There is work going on how to use advanced technologies for to provide high delta V. DARPA is funding some work in this area, JPL is doing, but so far we haven't done any of that. So if you look at the two, both Inspire and Marco, they actually don't have delta V capability. So they are actually launched by the upper stage. They are going on an interplanetary trajectory. So they're not using any onboard propulsion to provide delta V to get to Mars. Zero. So, so the short answer is that to your question is no, they don't have it. But you can imagine at some point you would want to have some delta V capability. So there is work going on in microelectric propulsion and a bunch of areas that can provide pretty significant, not huge, but meaningful delta V capability to do various kinds of maneuvers.
Thank you.
Yeah.
Can you provide some feedback on those CubeSats that are already been launched in low Earth orbit? In terms of lifetime, how do they compare to the expectancies?
Yeah, so very good question. I also didn't mention, I can also answer a question that is implicit here. We actually have our mission and safety assurance, safety and mission assurance directorate has an explicit effort on nanosats and CubeSats from a quality assurance point of view, safety, looking at the processes. How do we build these CubeSats so that they are as reliable as possible? The current generation of CubeSats that are being deployed and that are operational in Earth orbit are of the scale of between 6 months to 2 or 3 years. Some of the ones that we're building right now for Earth science, I would differentiate those missions that are doing real science, Earth science, and those are designed to last 2 to 3 years quite readily. We also have missions in Earth orbit that are being designed as tech demos. So those are not designed to last multiple years. They could provide the demo within 6 months to a year. But the whole issue of reliability and survivability long term is a concern, and that's why we have our safety and mission assurance looking at testing components, qualifying components. The CubeSats for Lunar Flashlight and NeoScout are actually using a rad-hard CNDH. I've seen it in the lab. It's a single board CNDH that is 300 K-rad tolerance. So it's a rad-hard processor that can go in a pretty significant radiation environment. So we are developing capabilities. Those are not your kind of cheap solutions, but they are, if you are going to go into deep space and into a more significant radiation environment, you'll need that.
Time for one more question. Yes, in front.
I just answer a question from before on the delta V. Our lunar ice cube is probably around 4,000 meters per second delta V with an iodine, solid iodine propellant ion drive, and if we took out our infrared spectrometer, we'd get up to about 11,000 meters per second. So significant delta V is possible. The solid iodine really makes a difference. You get a lot of power.
Thank you.
Thank you. Let's thank the speaker again.